Hello, my name is Holly Johnson, and I'm here to discuss exotic hadrons. Now, before I get into exotic hadrons, I wanted to discuss the history of hadrons. Now, some of the most well-known hadrons are protons and neutrons, which have been known to make up atomic nuclei since the 1930s. Now, particle physics became its own subfield in physics in 1947 with the discovery of pions and kaons, or K-mesons, at Bristol and Manchester universities, respectively. Now, despite not being discovered until 1947, pions were actually predicted by theoretical physicist Hideki Yukawa back in 1935. And he had predicted this to explain the range of nuclear forces that were being seen in high energy collisions, things like proton and proton collisions. Pions are actually produced in large amounts in these high energy collisions, which is why they were able to be predicted. Kaons, however, were not an expected result in these experiments. They were a new, strange form of matter. And the reason that they were strange was because they had some previously undetermined non-zero quantum number, which was found to be conserved in strong and electromagnetic interactions, but was not inherently conserved in weak interactions. And so this came to be known as the strangeness quark number. And kaons were particles that had a non-zero strangeness quark number. And so with this, we've started to understand what specifically hadrons are. Now, hadron is an umbrella term describing particles that are made up of quarks, specifically particles that have two or more quarks. Now, quarks are the smallest bits of matter, and they come in 6 different types known as flavors. They come in up, down, strange, charm, bottom, and top. And these quarks are never found in isolation due to color confinement. You will never be able to just pull away like one charm quark or one down quark and see it by itself. They're always confined to other quarks in color confinement. And so to actually see them, you need to be able to detect hadrons where quarks sort of live. Now, hadrons have two different subcategories. We have mesons and we have baryons. Now, mesons are hadrons that have 2 quarks, or more generally, they have an even amount of quarks. And baryons are hadrons that have 3 quarks, or more generally, an odd amount of quarks, minus having just 1 quark, as quarks cannot be isolated. And all hadrons are subject to strong force interactions. Some important features of hadrons and quarks are listed here. And so if we're going to talk about mesons generally, having 2 quarks typically are quark and anti-quark pairs. So having something such as 1 up quark and 1 up anti-quark would be an example of a meson. So mesons are more short-lived than baryons. And the more massive that they get, the more unstable they become. They have integer spin, which classifies them as bosons, and they have a baryon number equal to 0. Baryons are these quark triplets. An example of this would be a proton, which has 2 up quarks and 1 down quark, and are fermions due to their half integer spin. Their baryon numbers are equal to 1 or -1. And baryon number is conserved in interactions involving mesons and baryons. Now, mesons and baryons also have anti-mesons and anti-baryons. An example of this can be seen with pions. Here we have a positive pion, which is an example of a meson, that has 1 up quark and 1 down anti-quark. The anti-positive pion, or the negative pion, can be described as having a down quark and 1 up anti-quark. A proton has 2 up quarks and 1 down quark, and an antiproton also has 2 up quarks and 1 down quark. However, they are now all antiquarks, hence the bar on top of the letters here. Now, quarks are flavor independent in strong force interactions, and considering their baryon number, their baryon number will be positive for quarks and will be negative for antiquarks. Now, as more and more hadrons were being discovered, it was getting very confusing to organize them in a way that made sense. And so one of the ways that hadrons are organized is very ingenious, and it's called the Eightfold Way, which is seen pictured on the right here. And it's named for the Noble Eightfold Path of Buddhism. Now, the way that it's structured is that we have the isospin of these particles on the x-axis, and we have the hypercharge, this capital Y, on the y-axis. And these particles are placed in such a way that taking certain steps in the directions of this hypercharged isospin will actually replace certain particles with other particles. For example, if we take a neutral kaon, this K superscript 0, and move it one step to the right, we now have a positive kaon because we would have replaced one down quark with an up quark. And we can we could take any of these examples of hadrons and describe them using the steps that are placed here. Now, getting into exotic hadrons, there was only one mention of exotic hadrons in the textbook that I was using to learn particle physics. And that was, so in this following quote, the Q here is meant to describe any generic quark. It can be any of the 6 flavors. It's just used for conventional reasons. And Martin describes exotic hadrons as unusual combinations like 2 quarks and 2 antiquarks, and 4 quarks and 1 antiquark, which could give rise to so-called exotic mesons and baryons, respectively. And so what we're seeing with this tetraquark, which would be 4 different quarks, is an example of an exotic meson due to the fact that it has an even amount of quarks. And with our pentaquark, which are these 5 quarks, we're seeing an exotic baryon because it has an odd number of quarks. Now, exotic hadrons are defined by the textbook and generally as having 4 or more quarks. So approximately there have been 40 exotic hadron candidates observed experimentally, and all of the ones that have been observed have 4 or 5 quarks, these tetraquarks or pentaquarks. Theoretically, it is possible to have more than just 5 quarks. However, experimentally, that has not yet been proven. Given the newness of exotic hadrons, the subject of exotic hadrons in particle physics, there currently is no single universally accepted model that describes the behavior of exotic hadrons, specifically the decay pattern of exotic hadrons, their structure, and their spectroscopy. There currently is no one unified theory that can describe the behavior of these exotic hadrons today. Now, the first discovered exotic hadron candidate was called X3872. This was discovered by the Bell collaboration at KEK in Japan in 2003. And it currently does not have a different name other than X3872 because of the mystery that is still revolving around the subject of exotic hadrons. And looking at a lot of the other candidates, most of the candidates that we're seeing for exotic hadrons are charmonium-like. Now, charmonium is the combination of 1 charm quark and 1 charm antiquark. It's very similar to, it's just a certain type of quarkonium, where quarkonium is described as being a quark with its antiquark bound together. Now, many of the candidates for exotic hadrons are charmonium-like because they have mass in the region of these conventional charmonium states. And when these charmonium-like exotic hadrons decay, they've never been seen to decay without charmed quarks, which is another reason why they're described as being charmonium-like. Now, many of the exotic hadrons that have been found, in fact, all but 2 that have been experimentally found, have been exotic mesons because they are tetraquarks. As of today, there are only 2 pentaquark candidates, and those are the 2 that are listed here, which is PC4380 and then PC4450. Now, despite there not being many pentaquark candidates to discuss, and despite this, I still want to discuss some of the kind of interesting pieces that I found about exotic hadrons, specifically in the baryon number of these tetraquarks and pentaquarks. Now, if we're talking about conventional mesons, we know that the baryon number will be 0. And if we're talking about conventional baryons, we know the baryon number will be either 1 or -1. And so here I would like to pull in the convention that was used by Martin in describing the general format of an exotic meson, which is 2 quarks and 2 antiquarks, and the general convention of an exotic baryon, which is 4 quarks and 1 antiquark. Generally, the baryon number for a quark is 1/3, and the baryon number for an antiquark is -1/3. And so what we see with the convention that Martin has used is that these baryon values for mesons and baryons are conserved. for these 2-quark, 2 anti-quark system, we have a final baryon number of 0. And for a 4-quark, 1 anti-quark system, we see a final baryon number of 1, which would mean that despite them being exotic, they still have many similar characteristics to conventional hadrons. In conclusion, the study of exotic hadrons is extremely relevant and very interesting to particle physics as a subject. And despite it being so new, there is a lot of evidence. There's a lot of evidence that this, despite it being so new, and despite it not having a current unified theory, exotic hadrons are incredibly relevant and very interesting to the subfield of particle physics, and will be very important in the years to come in discussing the particle physics models that we use to describe our world on a very small scale. Thank you.